You know, we give them the very high stack.
I actually had it here. I don't want to be that big on yes, this is before we go party. Right. Oh, I was trying more than I've done that. We have the problem where it will be yeah, and they're like, yeah, you're perfectly back on here.
Magari controlla di
Exactly.
Or anyone. Ok.
Dicevano che online non sentono bene le domande quando sono da proprio, quindi se ti fanno una domanda
La ripeto.
ripeti.
Ok, perfetto. Ok. We're gonna give it one more minute for Ori to make some magic. I managed to collect people. Oh, it is a terrible placement for the timing. It's impossible to look at the time. Yeah, it's impossible. Like, I cannot see it from here. It's okay. Why don't you give me 5 minutes? Why don't we restart? I'm actually going to share myself during this first session. My name is Gisela De Rosa. I'm the mission scientist here for the Roman Mission Office. And I've worked on this talk together with Patrick Lawrence, who is the lead of at the Science Support Center at IPAC. So what I'm going to do is to give you an overview of the data products for WFI, what to expect, and how to access them. And I'm going to start here. Thank you. I'm not going to be able to see the timer, but that's OK. I'm going to start with an overview of the different levels. I'm never going to use just the acronym, but it's good, to start getting used to them. So we have 5 different levels that are characterized by different formats and different level of calibration. So we start from the level 0. Those are the raw packetized data that come down from the telescope, and those will only be available in master authorized account. You should not be needing to access them ever, but those then get processed and transformed in level 1s, which are the uncalibrated WFI exposures. So these are your 3D ramps. So they're data cubes, and you'll be able to retrieve them from the archive. The level 1s get processed to level 2, which are exposure level calibrated rate images. These are corrected for the detector effects, and they are collapsed along the time, so you have a rate image. The level 3 are the resample co-added images. These are your mosaics, practically. They're corrected for geometric distortions, and then they are co-added together, so they're deeper. Then we have level 4, which are the high-level extracted information. So this is a variety of data types. They go from catalogs, like source catalogs, variability catalogs, to all the spectral products. So your individual 1D spectra, combined spectra, catalog of spectra, they're all high-level, level 4 products. Then we have a final level that we're not going to discuss today, which are the level 5 products that will be the community-contributed products. Okay. Now, whenever I'm going to mention these today, I'll refer to these as exposure level, raw data, data cubes, I'll talk to them in explicit terms and always refer to the data level so that we start connecting them. Okay, so Roman has a very distributed project. We have different responsibilities all over the project. So I want to explicitly say who is responsible for what when we talk about data products. So here at the Science Operations Center, we're responsible for the creation and calibration of the WFI data cubes and the calibrated data rate images, so the level 1s and the level 2s. We create the mosaics, so your resample coadded images, the level 3s, for everything with the exception of all the data that come from the galactic bulge time domain. We are also responsible to create all the catalogs and the high-level products, so the level 4 that are associated with the exposure level and the mosaics that we create. And this includes source catalogs, photometric catalogs for the variable sources, and libraries for empirical PSFs. The SSC, on the other hand, is responsible for the creation of all the resampled and coadded images level 3 and catalog level 4 for everything that is related to the galactic bulge time domain survey. These include object and light curve catalogs, variability catalogs, microlensing, object and event catalogs. And similarly, they're also responsible for the creation and processing of all the spectroscopic products. So from your spectra to the catalogs that contain the information on the spectral data. Okay, so this is the split. And so Patrick Lawrence works with me on this presentation, and whenever you have questions, either one of us will respond. Despite the fact that we have 2 different centers that are responsible for these data sets, everything will be archived in mass, and the user support will be fully integrated, so it will be transparent to you. Okay, let's talk a little bit about the data format. The WFI images and spectra will be stored in the advanced scientific data format as DEF, so this will not be in FITS, and the catalogs will be stored in Parquet format. We use a tessellation scheme for our mosaics because, as you can imagine, we have huge data files, so we want to make sure that whatever we store is significant from the scientific point of view, but is still manageable when you work on the file. So what we do is to partition the sky in sky cells and projection regions. So the sky cells are square tiles that are 4.6 square arc minutes, and they are grouped into projection regions, which are 3.2 square degrees that share common WCS, and so you can have a consistent astrometric alignment over the full projection region. Now, these projection regions are squares along the equator, and they get more and more distorted as you go up towards the poles. All of this is fully documented already on our user-facing documentation system, our docs. So if you have questions, I invite you to log in and look for detailed information. Roman is a survey mission, so we'll have 2 kinds of products. We'll have prompt products and data releases. So the prompt products will be processed upon data received, and clearly they will be calibrated using the best available reference files and pipeline version at the time of the receipt. So which means that the quality may vary if you're looking for all the data in a survey that lasts more years. In addition, these are not versions. So if we reprocess them, they get overwritten and you'll only be able to retrieve the latest version from the archive. Then we're going to have data releases. Data releases will be reprocessed on a release schedule, more or less every 6 months after all the necessary observations are collected. They will be calibrated with a uniform pipeline and a consistent set of reference files, so that the calibration will be fully uniform, and all the products are versioned and archived. Let's talk a little bit more about the prompt products. So the prompt data products will be available in the archive as quickly as they are processed, with no access restrictions and no proprietary time. They will be available for everyone. So we'll have prompt data cubes, your level ones, within about 24 hours from the receipt of the data here at the SOC. This will include both the science data and the guide window files. And as I said, this will be, as they are reprocessed, they will be overwritten. Then we're gonna have the calibrated rate images, the level 2. This will be available within 48 hours from receipt. They will be processed with the best version of the pipeline, the best version of the reference files that we have. They might be reprocessed for data releases with a uniform pipeline and the reference file. And in that case, only the most recent version will be archived. However, all the information about the reference files, what pipeline version is used, is all contained in the metadata. So everything is always reproducible. We're also going to produce mosaics for your prompt products. They will be available about 5 days after we receive all the data that are needed to create them. And they will be created at the visit level, okay? Where a visit includes one or more exposures with consistent instrument settings, and they may include details or repeats, so they will be deeper than your individual exposure. They will be resampled on the SCAMAP tessellation that I talked before, but they will be at the native pixel scale. One note again is that the galactic bulge time domain prompt products will be created by the SSC. Okay. The high-level products, the level 4, so catalogs, source catalogs, and segmentation maps that are associated to the level 2, the exposure level, the mosaics that we create as prompt product, will also be available in the archive about 7 days after receipt of all the data that we need. They will, as I said, they will have source catalogs, but only single band source catalogs. And this is for the prompt products. So this will be available right after we receive the data in the archive. But then what we're gonna do is to reprocess units that make sense in a consistent and uniform way. So the data releases, the timing will be driven by the observation schedule. So the cadence will vary and evolve with the mission operations. Our current thinking is that each community-defined survey will have an independent data release. And this is because the observing strategy as well as the science are very different. So the data releases will be optimized for the science in that survey. The general astrophysics data releases may be grouped based on scheduling, with either the ones for the community surveys or individually. So if you look here, this is just an example cadence. We're still working on the mission plan. But for example, if we take observations for the high latitude wide area survey for 6 months, we might want to wait until all the observations are collected and then create a data release that contains all of those data processed in a uniform and consistent way. For the galactic bulge time domain survey and spectroscopy, the SOC will reprocess the low-level data, and then the SSC will create the higher-level data. Okay, more information about the data release products. Again, these are uniformly processed, and they are science-ready. They will be made available simultaneously in the archive. So they're not going to be trickling in as we produce them, but they will be unveiled all together, like data releases used to for other surveys. So one thing I want you to draw your attention on is the difference for the co-added images and the high-level data products. So clearly, we can the level at which we restart the reprocessing will depend on the pipeline and the reference files, and we can start at any level. If we create new level 1 and level 2s, this will be overwritten in the archive. Instead, the level 3s and level 4, so your mosaics and your high-level catalogs and science products will be versioned. The mosaics are going to be different than what we produce for the prompt products. So we're going to have a stack that is a full stack of all the images obtained for a program at a given pointing, okay? So it will be the deepest stack that you can obtain for that program at that given time. And then we're also gonna create subsets of image stacks that are tied to survey elements, and for the core community defined surveys, they will be optimized for the science case. Now, all the mosaics in this case, they will be resampled on the sky map, but they will be oversampled, so not at the native pixel scale. And for the high-level science products, the level 4, we are going to have more products. We're going to have, of course, photometric catalogs for time variability. We're going to have PSF-matched multi-band photometric catalogs. So in this case, we're going to have source catalogs in all the bands. We're going to have a small set of artificial source tasks, control systematics, and of course, segmentation maps. This is not an exhaustive list. This is some of the things that are included. How to access the products? Everything, all the products will be stored on the cloud in AWS, in the US East 1 data center, and they will be available through MAS in usual ways. So we're going to have the user interface. You'll be able to use AstroQuery as you use it for other missions. But one key thing is that for Roman, our images are much larger and the data volume is much larger than any other of the missions that we usually deal with here. So for Roman, we are planning to downlink an average of 11 tera of compressed data per day, okay? And if you compare the size of a full field of view, you can see that it's significantly larger than anything you've worked with, JWST NIRCam, for example. So clearly, there needs to be a change in paradigm to access and analyze the data. And our response to that is the Roman Research Nexus, which is the science platform that we are building, which offers low barrier access to data and collaborative resources. When I'm talking about resources, I talk about compute, storage, and software to enable your science with Roman. So the Nexus is, and we're going to see a demo, live demo of the Nexus right after this talk, is a deployment of the Jupyter Lab environment on AWS, provides you with cloud data access, so you'll be able to stream the data, work on the data without the need of downloading them. It has all the custom SOC software to analyze, process the data, visualize them, as well as plan your observations, and all the tools that we are creating are on there. And we're working to integrate the software created by the Science Support Center on the Nexus as well. It offers a very stable software environment through users and sessions. So you don't have to be concerned about that. You can just log in and do your science. It has accessible and scalable compute resources and a collaborative design and a pedagogical framework to help you transition from your usual workflow to a workflow that is cloud-based. Let's talk more about the collaborative nature of the Nexus. It's really built to be a collaborative hub. You'll be able to be part of a team, and that team will be able to share resources and be able to track the aggregated resources over time. You'll be able to be part of multiple teams, log in on a team, and have access to all the other files that are associated to you, to all the other teams. So all of that will be available to you every time you log in. And it also offers real-time collaboration features, for example, simultaneous editing, which is now in beta testing. Tyler will talk more about this, but we offer two kinds of approaches to our science functionalities. We have tutorials that are pedagogical Jupyter notebooks that show you how to use a tool or perform a specific task. And then we group these tutorials in science workflows and combine this tutorial with documentation and guide you through a specific science use case. For example, how to simulate WFI data from A to Z, how to analyze the data, how to plan for an observation. This is what we have currently as the offer, but we're working on developing more workflows as we speak. So just to close here on the Nexus, I want to say that as everything else, the Nexus is in active development, but has already been shared with the community for both training and feedback. We have given multiple workshops. Whenever you attend a workshop, you get a login, and at that point, you keep your login, so you can use it as much as you want. The public release is planned soon for late summer to early fall, which means that everyone that has an MyST account will be able to access the Nexus for basic exploratory work. And you'll also be able to request a team account that has more resources for your work. Everything will be regulated through a credit system that is very flexible. So we'll allocate credits to your team account, and you'll be able to spend them as you want on resources, so either compute, egress, or storage. And this is because clearly there are so many different use cases, and we're trying to keep things flexible. Okay, there's going to be a lot more on the Nexus in the future, but Tyler now is going to showcase its demo. This is my last slide, so if you have questions, please feel free to ask. This is my last slide, so if you have questions, further questions, you can check it. Questions?
Go back to the split between SST and SOC.
Yes. There you go.
So it's a very easy.
Don't worry.
It said 1D spectra there, and then some slide later it said 2D and 1D spectra would be provided as part of the L4 products.
Which one is it? Oh,
Both. It's both.
so it is 2D.
Yes, yes. Yes. All the spectral products.
Thank you.
There, Rob?
So, specifically about the Roman Nexus accounts, can you look at them, or do you have to be associated with like an institution like a Goddard or like an academic institution?
Anyone with an MyST will be able to log in.
Okay. So like the general public can sign up to go.
Correct. Yes. More questions? If not, oh, there.
Are there GPUs available on the?
Not currently, but we are investigating the possibility to offer GPUs. Clearly, in that case, you have a set number of credits. You'll be burning through your credits more quickly, but you'll be able to periodically request replenishment. We're also investigating the possibility of bringing your own AWS credits through third-party systems. It's all in development. If we don't have any more questions, no questions online, we're going to move to a demo. Oh, first year slides, you're right, sorry. Here we go. There you go.
Okay, so hello everyone. My name is Tyler Desjardins, and I am a principal staff scientist here at the Space Telescope Science Institute. So I'm going to be first discussing our simulated data products that we have available for you on the Nexus as of today. And then afterwards, I will take us actually over onto the Nexus and show you a bit about how it works. And let's go ahead and get started. So first of all, I want to highlight the simulations working group. So if you are interested in simulated data products for Roman, this is the forum in which we discuss those things about new data products, existing things, how we can update things, tools. So I encourage you, if you're interested, then please visit this QR code and sign up for the simulations working group. They meet every other Friday at 11 a.m. Eastern. All right, so right now on the Nexus, we have 3 categories of data products. And again, I'm going to stress this is what we have available as of today. We expect that this will grow in the future. I believe there's already at least one talk here at the symposium that mentioned providing simulated data products that would be hosted on the Nexus. So if you are interested in contributing data products for the community to use, please get in touch with us, submit a help desk ticket, and we will talk to you about how we can possibly host that data. But for now, this is what we have today. So first we have a realistic set of simulations that were created using Roman ISIM, which you heard Charles talk about earlier. These are compatible with the Roman pipeline, and these include the level 1. So these are those ramps that Gisela talked about, the uncalibrated data cubes. Level 2 are calibrated rate images. And right now we have a single example of a mosaic coad, a level 3 product. So this is a small set of observations that are a dithered set of observations around a globular star cluster, and we'll see that in a little bit. We have a direct image and a 2D spectroscopic image that were contributed from the high latitude spectroscopic survey team. I think this was the Galaxy Redshift Survey pit. So this contains a field of stars and galaxies. And then we also have from Open Universe. We've converted a set of from the Open Universe 2024 preview data set. We've converted that from FITS to ASDIF to help exemplify the ASDIF data format. Just to note that ASDIF data format, the ones that we use for the Open Universe files, are not compatible with the Roman pipeline itself because of the differences between how the Open Universe simulation worked and the Roman ISIM data products. But they're still an ASDIF, so you can kind of get a sense of maybe a more flexible generic use for ASDIF in addition to our WFI specific data products from Roman ISIM. All right, so a little bit more in depth about each of these. For the Roman ISIM data products, these, as I said, include the level 1, level 2, and level 3 data products. That means that you have the individual reads that contain all these effects like detector bias, cosmic rays, nonlinearity, specifically classic nonlinearity, bad pixels. We have the Roman PSF, the Roman band passes, et cetera, are all baked into this. The detector effects come from our analysis of the ground test data using reference files that are hosted in the Calibration Reference Data System, CRDS. What we don't include, though, for example, is 1/f noise, persistence, burn-in, or brighter, fatter effects. So there are some things missing from this, but Roman ISIM gives you a pretty good sense of what real WFI data would look like on orbit with a lot of the detector effects included. These can be processed with the Roman Science Data Pipeline, Roman Cal. And as I've said numerous times, this includes level 1, level 2, level 3 images around this globular cluster NGC 6535. So if you're a fan of NGC 6535, there you go. We also have some additional images that are for another tutorial that is in development right now. This is our time domain tutorial. So these include images from WFI-01, of a single galaxy and a supernova going off in a set of observations covering, I think it's 145 days or so. And we'll see an example of that as well. So here's what our Roman ISIM data look like. This is one detector. This is WFI-11. This is the level 2 file. So this has been calibrated for detector effects. And so you can see we have a mixture of stars and galaxies here, and you can see the core of the globular cluster off to the right in the image. And here is our lovely time domain example. So this is a type 1a supernova in the F129 filter over 155 days in 5-day intervals. So the workflow that shows you actually how to make this data is still being finalized. It is available in the Nexus, but we are still sort of beta testing this. And then we're also working on a follow-up tutorial showing how to do analysis of time domain data. Here is the example of what we have for our direct image and 2D GRISM image, showing you, again, the quality of the data. So again, this is a single detector, and we have a tutorial that shows you how to go through this and extract the 1D spectra. Now for the open universe data, I mentioned this is from the preview data set. So the full data set covers approximately 70 square degrees, of which in the preview there are 0.08 square degrees available. The full data set is about 400 terabytes. There's about 10 terabytes in the preview. This includes stars, galaxies, various transients, and was originally stored in the FITS format. So we've converted this to ASDIF, and we make it available through the Nexus via our S3 bucket that we have. It's Roman-like image quality, but it was simulated differently. So it doesn't have all the same characteristics that we see in the Roman ISIM simulations. There are 6 Roman filters available, and as I said, this cannot be processed with the data pipeline, but it's essentially science ready. So if you want to do analysis on the open universe simulation, we have that available. And again, just to give you a sense of what the the open universe data look like, here is a sample. This is a zoom in of a particular region on one of the detectors. And so you can see, we have some nice galaxies here, and we have some nice point sources mixed in. So the Nexus we're anticipating is going to be released by late summer, maybe early fall, sometime in that time frame. And these are just a sample of what we have today in terms of data stored on there. There's also other things. For example, we are fully connected to MASP, so if you wanted to bring in a JWST data set to go along with a simulated Roman data set and understand how that would compare, you do have access to other things as well. Everything in MASP is there, et cetera. And if you have other ideas that we didn't talk about today, again, by all means, please join the simulations working group and let us know what you're thinking. We'd love to have more data for more of the community to work with. All right. So now that I've said all of that, let's actually go over and take a look at the Nexus. So I have already logged in here and started up a server. So at the end of this, I'm going to show you what the login process and starting up a server looks like. It does take a few minutes. So in the interest of time, I've done this ahead of time. When you log in, this is what you will be greeted with. So it will always pop up this intro.markdown file here, which is the landing page for our documentation. If you are new, I am not, so I don't have this pop-up, but there will usually be a pop-up at the bottom right, which shows you an introduction to Jupyter. So if you're unfamiliar with using Jupyter Notebooks, Jupyter Lab, all these sorts of things, don't worry, we've got you covered, and there's an introduction there for new folks. Briefly, Gisela talked a bit about this already, and we also have a Getting Started with Jupyter here. But Gisela talked about the science workflows and the notebook tutorials. But you can go here and you can see, for example, all of the workflows that we have, those graphics that she showed, the workflows there. And we have some notes here about all these things, and these will actually take you to the individual. So if I click here, it will actually spawn the notebook itself. If I go back to the documentation, you can also see a list of all the notebook tutorials here. And more information, for example, about what data sets are available. So all those slides I just went through. We've tried to fairly comprehensively document all of this. So please, if you have access to Nexus already, or if you're waiting on access, when you get to it, take a look at the documentation. It should help, and if it doesn't, let us know. So next, I'd like to actually show you one of our tutorials briefly. I'm not going to run through the whole thing. But when you get to our tutorials, we have a lot of information about what the goal of the notebook is. We talk about the imports, why we're importing them. And I'm going to go ahead and start running some of these. This is our working with ASDIF tutorial. So if you're new to the ASDIF data format and you're saying, well, what the heck is this? How do I work with ASDIF files? I love FITS. Check this out. We talk a lot about the advantages of ASDIF, why we chose this, and how it's helpful. We give a lot of links here. So for example, there is this link here will take us to RDocs and talk about what is ASDIF, why are we using it. And down here in this cell, we're actually going to connect to our S3 bucket, which is a storage solution for AWS. So we are reading an ASDIF file into memory here, which might just take a second or two. And then as soon as that's done, there we go. We can take a look at what's actually in the ASDIF file. So in this case, you see this is truncated here, but we have our metadata and several arrays. We have data, data quality, error, Poisson variance, read noise variance, flat variance. And so we can take even deeper looks here at what we've got. So we can see our data array is a NumPy array, float 32 with shape 4088 by 4088. We can take a look at all of the different arrays and dictionaries that are in the file. So if we didn't want to look at this full description, this nested description here, if we just want to know, well, what keys are in here, how do I access them, we can do that. Same for the metadata, and we can see all the metadata tags here. We can ask, what is the primary array name? So if we're unsure, is it called data? Is it called science? Is it called something else? ASDIF actually tells you this is the primary array that you should be interested in, that the author of the file said this is where you want to look. In this case, it's data. And of course, we can confirm that data is a NumPy ND array. We can take a look at some values from there, and finally we can actually show part of the image. So this is just a small cutout of what our file actually looks like, and we can also look at a histogram of the values. So this is where I'm going to stop it for this tutorial. If you're interested, the notebooks are available on GitHub, and they're all loaded in here into the Nexus, and every time you log in, a fresh version of the tutorials with the latest updates has been synced to your account. If you don't want to get to those from here, from the documentation, you see we also landed in this directory here with notebooks. And so we can click there and we can see all the different tutorials here. And you also see, for example, RIST, which Charles talked about earlier, is in here. We also have our Pangaea tutorials, how to run the pipeline, etc. So hopefully when you all have access to the Nexus, if you don't already, you'll get in here and play with things, and maybe even some of you will be able to contribute to it. The last thing I want to show, well, next to last thing, is our real-time collaboration. So as Gisela said, this is in development still. We're doing some beta testing right now. But the idea here is that you'll actually be able to work together. We're still trying to understand some of the use cases here. But we did want to implement the system in which multiple people will actually be able to work on files together. That could be a text file, that could be a Jupyter notebook. So we've got an example here of a simple Jupyter notebook. Oh, and you can see my notebook tour popped up. That's great. So we're going to do our imports here. We're going to read in our ASDIF file from our S3 bucket. And we're going to simply plot an image here. And so we've made some initial choices which are maybe not the best choices. In fact, I'm going to mess with this a little bit. And I'm going to change this. And I'm going to run this. And we've produced this lovely, very blown out image of the WFI. I know, we could probably do better. Yeah. So Gisela here, as you can see, is changing some of her values. I'm not doing this. This wasn't pre-recorded. So we're changing our scaling here from 0 to 5. And oh, I think you missed a D there. So let me fix that for you.
I think we should also plot the whole image.
Oh yeah, this is just a zoom in. So yeah, so why don't we change this?
Let's do this portion.
And as you can see, this time Gisela actually compiled the cell. I didn't. So the changes she's making, I can see in real time. I can see both the edits she's making to the code, and I can see everything that she's run. So we're actually working on this together. So this is what we're trying to implement right now to help you all work better collaboratively in the future. If you have use cases for this, we would love to hear more about what you would like to do. So please get in touch with us and let us know. So finally, I'm going to log out of the Nexus. I'm going to actually shut down my server. So best practices here, I'm going to go to Hub Control Panel. I'm going to say stop my server. And I will even log out here. So when you come to the Nexus, our landing page right now looks like this. If you don't have a MyST account, then there's a big button saying create new MyST account. You probably already have one if you've ever been on an APT proposal or anything else. So check to see if you have one. Someone may have made one for you and you just didn't know. And then if you have a MyST account, you sign in with MyST. This will take me just a second here. And I hope I typed my password right so we don't have to do this again. Yeah, don't remember me. And for security purposes, I gotta do my two-factor here. Everyone always loves this. And that will get us to our launcher. Hopefully this. Okay. All right, so this is what the launcher page looks like. This is probably going to change a bit in the future, but for right now, you'll all have a personal server, and you'll be able to select from a few different options here, depending on if you are coming from a funded program versus if you are just doing some exploratory science. You'll have some different options. If you're on a team, you'll also see team options here. So I'm on several teams here, and so I can select a team server and spawn that. So if I want to say this should come from a particular team's credits, that's how you would do that. And so you would click this, and then down here at the bottom, you would say Start Server. This will kick off a process that takes several minutes to complete, so I'm not going to do it right now. But if you have any questions about how this works, please get in touch with us, and we'll be happy to help. All right.
Thank you. We have time for a quick question.
So is the idea that when we apply for data analysis in a proposal that we have to estimate how many credits we need, or how is that going to work?
I will.
Julie, do you want to?
So the very quick answer is we've no idea. But let me expand on that slightly. And that's in part because we don't yet know what fraction of people's analysis are going to be a good fit for this environment versus something else. And we're working closely with the existing Roman science teams to sort of figure out what they're doing with an expectation that will give us insight into what the community at large are going to do. We know we need to have established this by the time of the call for proposals. So we're working on it, and it is kind of very high on our list of things that need to get nailed down.
Robin, ideally, will be able to support additional allocated resources on the Nexus if it is identified to be the right solution.
Right. I mean, there will be a very large number of use cases for which that is the right solution.
Absolutely.
We just haven't yet quite figured out what the mechanism is going to be.
Other questions? Patrick.
So for the servers that you can choose, is there documentation that's available right there to like know kind of what somebody who doesn't know what they're doing in the cloud, like to know how much RAM do I need?
That is a very good point. It's at the top of our priorities before we go public, and you're going to have examples of what to pick based on your use case and how would you trade it to be used.
Okay.
Yes.
I'll add, it's a bit of a chicken and egg problem here because I showed you all the documentation was in the Nexus once you got in, right? So we're also adding documentation to our docs about the Nexus. So there'll be some high-level overviews there before you even get into the Nexus.
Okay, so if you have more questions, we'll be here the whole day and we're available, so please reach out. Thank you so much. and we're gonna have talks and presentations from 4 of the pits, and Hyun will be starting. Here we go.
Is there a pointer?
You can use the.
Is this a pointer? No?
No, it doesn't have a pointer, but
Okay,
if
all
you
right, it's
need,
okay.
you can
Yeah, I'll
use-
just use my finger. Yes. Yeah, I was kind of whispering since I haven't started yet.
If you want to point here, if you're here with the
Okay.
cursor, they will be able to see.
All right, I'll just use my finger. Okay, hi. Hello again. I'm Yung Wang. So I'm presenting the scope of work and deliverables on behalf of the Roman Galaxy Redshift Survey Project Infrastructure Team. So I'm doing it as a PI this time because it's really our first presentation to this community of Roman science. We did a AAS one, but I think maybe because of the higher registration fee, so there's a lot less people there. So we hope to reach a greater community here. So first, beautiful picture, right? So it was made by my former Roman postdoc, Zhong Xuzai, whose name already appeared several times at this meeting. It was excellent. So Roman will be fantastic in extending our reach in the 3D universe beyond ground-based surveys. That's why we go to space. And very brief reminder of why the Roman GRS, Galaxy Redshift Survey, is fantastic, right? So if you already heard the buzzword BAO, Baryon Acoustic Oscillations, I won't beat on that. And also, Hee-Chang will give a talk about DESI tomorrow. Why do I hear the beeping?
Sorry.
Oh. Okay, yeah. So BAOs are basically standard rulers calibrated by the CMB. We heard fantastic talk about CMB earlier. And we will be able to measure expansion history of the universe, h of z, and also the angular diameter distance, which is the integral over that. Right, so it's a geometric measurement to tell us if dark energy varies with time or not. So, DESI published some beautiful BAO measurements that made headlines everywhere. The other thing you may have heard less about is that the fact in mapping out the 3D universe, we cannot measure the distances, but we use redshifts, actually works in our favor because the artifacts in redshift space on large scales, the great Nick Kaiser, late Nick Kaiser showed that these actually tell you the growth rate of large scale structure. Okay, so to know what dark energy really is, if it's even energy, could be modification of general relativity. How do you know for sure? Well, you measure growth history of large scale structure, then you can tell. And weak length and galaxy clustering give you actually 2 different probes of how gravity might be modified. So we need both. All right, so I want to read what's here, right? So these are the key numbers that you've seen several times of the Rotec blessed GRS for Roman. Okay, so now here's my dream team. Why do I say it's my dream team? Because has the key experts from DESI, also key people from Euclid, right? What else could I ask for? So we have this fantastic expertise that we can leverage to do the best we can for the Roman GRS. This is what you really care about, of course. So this is just from our proposal. And so the only things that have changed is really the timeline, because when we proposed was guesswork, right? Now we are actually, well underway in all of our tasks. So we've defined tasks based on the deliverables that we've identified. I will not, you can read better than me, right? It would be boring if I just read what's on the slide. So basically, we are going to deliver everything you, the community, may need if you would like to use the Roman GRS for cosmological science and galaxy evolution science. And then, of course, our work is really centered on enabling us to make these deliverables for you. And so, right, so here are the tasks that map to the deliverables. And I put it in color-coded categories. Apology to people who might be colorblind. So, but anyway, you see, right? We cover everything that we can think of. We simulate the data. We simulate the observing program so we can help optimize it. And we study systematic mitigation, because otherwise, how can you trust the results you get, right? Then, very importantly, we are committed to delivering high-level data products to the SOC. Okay, so you can see the range. So these cover the usual bread and butter things in cosmology for those of you who are cosmologists, right? 2-point statistics, 3-point statistics, maybe even 4-point, we'll see, right? So that, and we will release the codes and covariance matrices and mocks, both high-resolution mocks and to simulate the Roman GRS, and lower resolution ones for you to calculate the error bars, everything you can think of, and the joint analysis. And now, what you may not have expected would be, we also have high-level data products in general astrophysics. So, right, so that we have, also leading experts in galaxy evolution on our team, whom I recruited, so that the Roman GRS pit will serve the entire community covered who benefit from this GRS. So it's not just a cosmology pit. Really, we try to be as broad as we can. So of course, we provide support to the science centers and the Roman project, ASAP. So I personally need that, so I basically respond to requests, well under a day, usually, if I can manage it. So now I'm gonna walk you through the status and highlights from tasks 1 to 10. Those are the technical ones, tied to the deliverables. So our top priority task.
You have 5 more minutes.
Oh, okay. Our top priority task is GRISM simulations, which has been mentioned and alluded to numerous times. Okay, so now, what are we committed to? We are committed to provide the realistic Roman GRISM simulations required by the SSC to do their final round of the R4 testing of the spectroscopic pipeline, the official thing. Okay, so, and we hope to have something by the end of this calendar year. The other thing we are committed to is to make a public tool for you all to go simulate Roman GRISM images. And so we hope, we plan to release the first version about 1 year from now. So a lot of work, as you can imagine, right? But so then, so what have we done here? Well, look at the pretty picture. So the top are the direct images, right? So the on the left, it's just stars. On the right, and we add galaxies, right? So stars are really important for calibration, as you can imagine. So in the previous round of science teams, we were only able to simulate one kind of star, but now we actually have a realistic distribution of all spectral types. It's really beautiful work. Then okay, also we now switch to using Grizzly, which is a public code, so then we're gonna develop that for Roman and make it, open source well, it's already open source. So what we develop will also be open source and user friendly. And we actually now have a core group of people on our team. You can see their names there who work on this tirelessly. Okay, so now highlight of a major progress is that thanks to Keith Barkos, who's undergraduate student, can you believe it, at Yale, who's led our effort to include wavelength-dependent PSF. So the SSC absolutely requires that to test the pipeline. So very excited about that. And so Ashley will give a talk about algorithm simulation work tomorrow. And Keith has a poster that he previewed yesterday, I think. Yes, I will. All right, that's top priority. So now to run through the other ones, modeling galaxy population. Okay, well, we have two different efforts and they all tie together. And then the goal is really to integrate the realistic astrophysics into algorithm simulations. So, our simulations will serve the galaxy evolution people as well. And Mark's, fantastic work. Andrew Heron gave a beautiful talk where he alluded to that. So he already delivered a prototype for the Roman GRS Mark that team is playing with. And we do plan to release within a year the 2400 square degree Roman Mark for the whole community to play with. And so Ashley also did this work well over a year ago, right? So we do have this tool to help optimize the scheduling of the Roman GRS. And so we also are committed to do the relative flux calibration so that our cosmology will actually be robust. And of course, I mentioned we model systematics. And right, so this is the bread and butter for cosmologist part. 2-point statistic, 3-point, right? We're making progress, on every single of these tasks. Then that's my final slide, okay? So you guys can get all excited about this. I want to mention, so you keep on seeing that, oh, the ROTAX tells you we can have more than 19 million galaxy redshifts from Roman, but actually only 10 million have two emission lines, which is, required for robust spectroscopic redshift measurements. So those are above redshift 1. So there are 9 million, which are below that. The good news is that James Kober found that about 20% of those H-alpha emitters at the redshift below 1, 9 million of them, right? 20% of them have a detectable sulfur-3 line. So yay, we just boosted the number of galaxies we can use for cosmology already. Then, of course, you heard about Euclid. Euclid only has one emission line, H-alpha, for most of the galaxies. So, of course, our team will be working towards, some way to make use of the 80% of the 9 million, which only have one emission line. We will, do something so that none of those will go to waste. Thank you.
So I'm going to go for one.
Oh, so feel free to, ask me or anyone on the Roman GRS pit questions anytime. That's another reason I want to come up here and give a talk instead of, have someone else so you know who I am, right? So.
Perfect. Thank you so much, Hyun. The next talk.
Okay. Oh, I got my own, I think.
Oh. And we have Eric Peterson, who's going to talk about the supernova cosmology.
Yes. Hello, everyone. Can you hear me all right? Great. So again, I'm Eric Peterson. I'm a postdoc at Duke University, heading to Michigan next month. I'm so thankful to the Supernova Pit for inviting me to give this talk, as well as the conference organizers. So I'm hoping to give a big update from our Supernova Pit. There's been a ton of work that I'm going to talk about, and when I say we, it's most of the time not me. I've only done a little sliver of this work, but just super proud of this team and hoping to get through a good amount here. So I'm going to try to go quickly here. To kind of motivate what we're expecting and what we're excited about with the Supernova Pit it was made kind of apparent, and you've seen this already from the DESI cosmology results, where if you're looking at WCDM, you combine your various probes, including your choice of supernova sample, you're going to get tight constraints on your cosmological parameters, but you're going to see that in WCDM, our W is consistent with the cosmological constant. But when we look into a W0 WA space, we see potential 3 sigma tension with WA equaling 0. So this is an exciting time for supernova cosmology. What we're expecting from Roman, again, we're super excited for the contours that we're expecting. From Rubin plus Roman, this is kind of an indicative contour that we're expecting. And to look at the survey itself, again, I keep saying it, we're super excited because we're going to get unbelievable statistics from the high latitude time domain survey. So we're going to get both great quality. These are some representative light curves here that we're expecting from Roman, out to high redshift, great quality, as well as quantity. If you look at the expected sample that we're going to get from the time domain survey, you're going to see very high in redshift, as well as huge numbers as compared to what we've gotten from Pantheon Plus, for example. So that's the redshift histogram there. And then what we've promised as a part of the pit is this full pixel to cosmology pipeline. I don't want you to read this whole slide, but we're getting our simulations, go through photometry, classification, calibration, and characterization. And I want to step through kind of some of the pieces that we've gotten updated since the last time we've given a talk as a part of the pit. Again, don't read this whole slide. We've got a ton of deliverables as a part of this pit, and we're progressing well. That's one of the big takeaways that I want you to have. We're progressing well. We're super excited for this survey. Speaking of some of the things that we've gotten out recently, here are a few paper announcements from this past month. One from Lauren Alderodi on the photometric pipeline that we're working on, as well as from Ben Rose, one of the leads of the pit, on various transient statistics that we're expecting, as well as from David Rubin back there, looking at trying to optimize the high latitude time domain survey, as well as the cosmology constraints from Rick Kessler, among others. Of course, all a part of a team here. So we're excited about those paper announcements. And then to step through just a few of our teams here, in terms of photometry, you heard the talk from Lauren earlier on Monday. There's a few different photometric pipelines that we're looking to work on, or to deliver. One of those is Frosty, as well as another one from scene modeling photometry. And the reason why we have multiple pipelines is for different purposes. From Frosty, again, Lauren gave this talk already, so I won't go into it too much. But the point here is trying to be fast, optimized to work on a GPU, to be able to get light curves very, very quickly with Frosty. And so here, this was, again, work that was worked on with NVIDIA to optimize on a GPU. We've been able to observe or obtain light curves and match them up with the input light curves very well for 200 supernovae already, and we're scaling that up imminently. This is some work on the scene modeling side from Cole Meldorf, among others, to have this be the post-survey photometry that we're looking at, so it's going to be more precise. You can see up here in this first image, this is a simulated image, and then we're comparing with scene model, forward modeling the background as well as our transient here as well. And you can see that once you subtract out the background, the galaxy is pretty faint to the left of the transient there. You're getting noise as well as your supernova right there. So this is progressing well on the scene modeling photometry side. All right, so spectroscopy, this is one of the most recent, largest updates on deliverables that we're excited to share about. The big difference, so the SSC talked about spectroscopy deliverables. They're going to have, the big difference for us is we've got extra contamination from the transient, the supernova on top of these galaxies that we're trying to disentangle. And so that's an extra level of difficulty that we're working through. And so here, this is a team, our spectroscopy team is led by Russell Ryan, among others. I'm not sure if Russell is in here. He mentioned he may be. But I'm super excited about learning more about this. You can see right here a little GIF here of the source image with the transient as well, and then subtracting out the science from the background from the science. And what I think is real state-of-the-art, super cool to learn and hear about is these data cubes that the spectroscopy team is working through. And so what you can think through is the two-dimensional is if you have a spectrum at every single pixel location, so that's your 2D, and then every single pixel has its own spectrum. We're getting these data cubes constructed from using the roll angle of Roman itself to construct that data cube. So I'm excited that these results are coming out now. And so this right here, this is kind of the most into the weeds slide that I'm going to show here on the spectroscopy team, because it's been the latest, largest input or added dimension that we've had in our team lately. What you can see here is if you only got half of the data, so if you only stepped through 0 through 180 degrees for a given galaxy or given host galaxy, how well could we reproduce what we would expect or what we will see from the other 180 degrees through the roll angle there? And what we can see is comparing truth to our simulated extra half of the data, you can see that subtracting those off, you're getting great noise. So we're super excited that only looking at half of the data, we can actually reproduce the other half of the data. And so this is top-notch stuff right here. Okay, and then this other little GIF here is just showing how this is one of those example data cubes where you've got your spectrum at every single pixel location. And you can see as I step through wavelength here, you can see various emission lines as the galaxy brightens in various wavelengths. Super excited about that. And then there's other kind of less state-of-the-art, more traditional methods, direct modeling and SED modeling that's progressing really well as well. Okay, so supernova systematics, this is more in my area or my department. This is some work that I've been working on as well as other areas. The point with supernova systematics, we've talked about it on Monday a lot, is we're getting into the systematics dominated era. And so we want to try to figure out how much of the supernova intrinsic scatter, how much is truly intrinsic to the supernova versus extrinsic things that we can model. Okay, great. So please come talk to me about my intergalactic dust work. This is one of those systematics we're trying to model to see if we can measure intergalactic dust with Roman by itself. This is something that LSST can't do alone, and so Roman is going to provide a measurement or an estimate on intergalactic dust that will be used for a systematic with LSST. This right here is trying to see how well we can reproduce the model given various calibration systematics. And what you can see is if you get variant shifts in the filters, 0 points or the filters themselves, we have to get down to about the 2 millimag systematic or 2 millimag calibration in order to avoid a big significant drop in the figure of merit. So our calibration that we promised millimag, we really need to get to that. And so the last thing I'll say here on calibration is that effective filter, this is some testing we're seeing. We're seeing that we can model this calibration and get down to that millimag level. And then finally, that was work from Purohit and Dylan Brout. And then finally, work with Vivian Miranda, among others. We're working on a cosmology emulator. And the point being that it's fast, and we're not looking at just supernovae. We're looking at other cosmology as well as other probes. So not just lambda CDM, but other cosmologies as well. So I'll leave you with my conclusions there. Try to get through a lot of it. Thank you for your time.
Thank you so much. Questions? Questions of can I ask you, so for the work that you're leading, what are the milestones you expect in the next 6 months?
Yeah, are you asking me specifically about the intergalactic dust portion?
Yeah, that was very.
Yeah, come talk to me on my poster for sure. Anybody can. Yeah, hoping to submit within the next few months for sure. But we're propagating to see how much this impacts cosmology, and then using it to see if we can constrain intergalactic dust using just the supernova color evolution. So thank you.
Nice.
Yeah.
We'll come over to your poster. Any more questions? If not, thank you so much. Yeah, there we go.
And back to slide one. Yeah. Let's go to slide one.
Okay, so Sean is gonna give us an introduction for the ARGIS.
Thank you. Hello, everyone. Sean Terry, Assistant Research Scientist at UMD and NASA Goddard. And I feel the need to quickly apologize for interrupting such a great cosmology conference with a talk on exoplanets. If you have complaints, please direct them to gowdy1@osu.edu. Okay, so let's get started. So the yeah, the Roman. Yes, yes. He loves No, he loves feedback. So send Scott all the feedback. The Roman Galactic Exoplanet Survey. So as the name suggests, so it's a PIT that's supports the exoplanet microlensing science case for the Galactic Bulge Time Domain Survey. And so I'll quickly note, we do expect, as Tom said, a huge amount of transiting exoplanets in the GBTDS data, but our PIT and this talk will primarily focus on the microlensing science case, exoplanet microlensing. So the PIT, the PIs are Scott, that's who you send your complaints to, and Dave Bennett at UMD and Goddard. Our membership is about 75 or so. Primarily in the United States, but we have a pretty significant fraction of international collaborators as well. A lot of working groups. Of course, I don't have time to go through all the details of each one, but if you see one that looks interesting, feel free to ask me later, and I can give you a fun fact about working group. We have a website, argus-pit.org. It has a ton of information on any publications that come out of our PIT, any other details, news. So again, it's probably not the perfect audience to advertise this to, but our PIT is hiring a postdoc right now. So if you know anyone, or if you are interested or know anyone who might be interested in working on Roman exoplanets, this postdoc job ad, it's also in the AAS jobs register. It'd be working with Jesse Christensen at IPAC and Caltech on the planet occurrence rate pipeline through the PIT. So the next few slides, I'll just give some updates on recent activities, some data products we've generated as a PIT and delivered, and some upcoming plans. As you can imagine, stellar variability is very important when you consider transient, stellar transient phenomenon like microlensing or transits or anything really. So our working group 6, variable stars, generated catalogs of thousands of variable star light curves. This is just one example on the right, just showing a long-term stellar variability trend. And in there in red are the GBTDS seasons. with or without microlensing events injected in them. So a lot of these catalogs have been shared already with some external groups, like many collaborators in the Rubin consortium are interested, as you can imagine, in variable stars. Other funded wide field science teams also interested in variable stars and their stellar variability, how it affects light curves for many different things. Another group, the Working Group 7, so it's kind of dedicated simulations of microlensing events in Roman. So many thousands of events have been generated in several catalogs. This is one example. So this is slightly outdated, as Tom mentioned. In the gap between the first 3 and second 3 years for the overguide strategy, we expect actually some lower cadence data on the GBTDS in there. But that's a microlensing event simulated with a little planetary signal injected. Maybe hard to see in the figure, but it's a pretty high SNR signal from a planet. And these have been shared with the Microlensing Science Operations Service. I always forget the last S. The MSOS pipeline. It's a sort of the official microlensing data reduction pipeline, microlensing catalogs that'll be published as part of the SSC. So of course they're very interested in validating and testing their pipeline, which will be the official pipeline on simulated Roman microlensing light curves. These all have realistic photometry, noise models for what we expect the Roman photometry, the passbands and filters we expect for the GBTDS data, and all of that good stuff. And we are planning to publicly host a lot of these catalogs very soon. One that's kind of close to me, I'm a co-leader on Working Group 8, so it's simultaneous and precursor observations of the GBTDS fields. So I'm leading a pretty large Hubble program that's ongoing right now in cycle 32 and early next year in cycle 33, that's taking many hundreds of small HST field images to cover quite a large majority of the GBTDS, the Roman fields, at least the 5 connected fields, not the GC. If you want to ask about the GC, I can explain why later. Maybe some ideas with JWST upcoming. And so there's many cool science cases for a precursor survey of these fields, things like high resolution extinction maps with HST. My personal favorite is thinking about the science case where Roman detects microlensing events during the prime mission, maybe in the late 2020s, later this decade. We have these high resolution data sets we can go back to with Hubble, and actually Euclid also has done a bulge precursor survey, and kind of in search for these lens objects many years before they've actually caused the microlensing that Roman has detected. That's just one example. Another quick one is an input catalog of stellar point sources, dozens of millions of point sources. Similar to, again, kind of on the exoplanet side, the Kepler input catalog was very important for Kepler studies, or the KIC, as it's called. Also, TESS had an input catalog, the TIC. So maybe something like an idea like the RIC, or the Roman, or maybe the RBIC, Roman bulge input catalog. Anyway, so very cool ideas that can be done with sort of a precursor data set before sort of the GBTDS has its own catalog that it'll generate, of course. A few more continued. A few months ago, the PIT held a microlensing mini course, which was very fun for students who are incoming to do Roman-related research experience for undergrad projects that they're currently working on this summer. But a week right before they all started their various projects, we held this mini course online. So virtual lectures. It was a week long. There were 5 chapters, chapter each day. All of the video lectures were recorded. All of the PDF, the curriculum material, Jupyter notebooks for example fitting microlensing light curves, all of that good stuff is now hosted on our outreach page on the website. So any new students or anyone new that wants to get involved, in Roman microlensing will have that as a resource that lives on the page. A few things coming soon. We have plans right now. We're performing a microlensing data challenge. That's working group 9. And so some of the details are still being worked out, but it'll likely be in coordination with the T-REX's data challenge. So this is the transiting exoplanets in the GBTDS. It's a separate funded WFS team, but there are, of course, similarities. We'll both be utilizing the GBTDS data. So later this year, we expect these data challenges, potentially hosted maybe on the Research Nexus, to be sort of run either in parallel or jointly with some fun prizes for data challenge winners. And then lastly, our pit, we have annual in-person, one in-person meeting per year. The next one's coming up in a few months in October at Ohio State University, and this year will be joint actually with the T-REX's WFS team, which should be great. Okay, so my last slide is a comical attempt at putting cartography, which is in the title of this conference, in context, at least for the GBTDS. So sort of Milky Way cartography. So as Scott likes to say, by the end of the GBTDS survey, these fields will be some of the deepest exposures ever taken of the sky, integrated across the whole survey. And so when you combine a large telescope like Roman with orders of magnitude more observing time compared to something like Gaia. So we know Gaia has done very well for, mapping Milky Way cartography in our galaxy. We also know Gaia struggles quite significantly in highly crowded regions like the disk or the galactic bulge with millions and millions of stars, very crowded. And then of course Roman's IR sensitivity. So if we combine all of this, we'll get extremely deep populations into the galactic bulge and very likely the far side of the bulge in possible disk of our galaxy through some of these fields. So we can really attempt to kind of do some 3D cartography of these stellar populations through the galactic center region. And the very last point, over time, it's obvious, but there's ground-based microlensing observatories and surveys that have been running, some of them for 30 plus years. Roman, the first dedicated space-based microlensing survey will really, be revolutionary for things like understanding the microlensing event rate by stars, but also not just stars. Anything with mass can act as a lens. So a free-floating planet, an isolated black hole, which are nearly impossible to study, given they're isolated, and other optical depth studies in these, very highly crowded regions. Okay, thanks. I'll just put up some of the QR codes and take any questions.
Questions?
I have a question, I think, about the variable star catalog. I'm wondering if there's some kind of accreting binary or something that goes into outbursts, so it looks like a transient. Will you guys be able to find that in post-light curves?
That's a good question. So we have quite a large variety of different types of variables. I don't know if we have any of those specific, they're different than cataclysmic variables?
Well, they might be cataclysmic variables, but they're so faint that they're not detected in quiescence.
Yeah. So maybe would they be in a catalog, like a reference catalog for? They'd be too faint. They're not even in a catalog. Yeah, it's a good thing to consider.
So I wonder if that would be covered in your variability.
But it'll be anything that's variable, that's non-microlensing, will be in the variability catalog that is being produced.
But it needs to.
It won't be separated out as specific types of variables.
And you just need to detect it once, anytime in the survey.
Anytime in the survey.
Yeah. Okay.
So there will
Just
be
have to be variable one time in the survey.
Great. Thanks.
Yeah. So like ROI or anything else.
Yeah.
Perfect. No. Perfect. We're gonna start with our last talk. Thank you so much.
Tommy will present the high-latitude imaging cosmology.
Yeah, so I'm Ami Choi. I'm going to stand in for Olivier Doré, who unfortunately couldn't come in person. Excuse me. And then I will be also presenting this along with Tim Eifler on behalf of the High Latitude Imaging Survey Cosmology Project Infrastructure Team. All right, so luckily we can go very fast through a lot of this background, since also I know we're the last presentation holding you back from eating. But yeah, we are, our main science goals are to measure weak gravitational lensing, and then also galaxy clustering from the imaging side. And then, so that's kind of the left two boxes here, and then of course, we're also combining all of our knowledge with what Yoon's team is presented, and also what Eric presented for the supernova team. So together we kind of get this picture of dark energy, dark matter, and possibly modified gravity. Okay, so I'm going to really just skip through these because you've heard a lot about this already earlier throughout the symposium. And so here's a little schematic that Tim made, just comparing sort of the history of cosmic shear or dark energy surveys as a function of time on the x-axis. And then they're all complementary. So we're really now in that farthest right part. And we've also heard a little bit about this before, so I won't dwell there. And then also earlier, Tom talked about the core community surveys. And so what we're really focusing on is the high latitude wide area survey from the imaging side. So here's some like what the ingredients of that are, and then there's different kind of levels of that in terms of the area and depth and filter coverage. All right, so maybe I'll also skip this, but we do have a lot of overlap with other surveys, so again, very complementary. And then this is a, I would say now outdated plot, which shows wavelength coverage on the x-axis and then the depth on the y-axis, and then some of these numbers probably need to be updated for the recent the community survey design. Okay, but our overall goal is to develop, implement, and validate a weak gravitational lensing measurement and analysis and infrastructure, really. So these are pipelines that would allow us to process the first year of high latitude imaging survey data, and then eventually reach the dark energy parameters at the end. So we are really needing to streamline these tasks. So we're trying to think about all of the cool science that we could do later, but really for the purposes of the infrastructure team, we're deferring non-essential tasks to future work. But we do want to lay the foundation for example, joint analyses with other cosmological surveys, and some of these cross correlations have been discussed already in the symposium. And so really our deliverables start with the data sets provided by the SOC, and then we produce catalogs of calibrated measurements of shear, and then some other observables, and then that goes into an inference pipeline, and then we derive cosmological parameters. And so all of these codes and catalogs and statistical measurements will eventually be made public, so that other groups can also work with these to do their own analyses. And then, we would like to also prepare people to do sort of beyond the standard dark energy analyses. All right, so just a quick look at what our proposal team looks like. 38 scientists, but many of them are actually new to Roman. And then we do have international collaborators from France and Japan. And we've grown a lot in the last year. So we have a lot of graduate students and even some post-baccalaureate researchers and postdocs. Here's our website, so please go there for more information. And here's some team photos from our last PIT meeting last October. So this is at IPAC. And so you see everyone kind of on the left side and then our junior members on the right side. So since we're here this week, I wanted to point out our various early career researchers who are in attendance here. So if you see any of these people here or also out in the wild, not here, please talk to them about science, offer them jobs, et cetera. But there's also these other people down here, and I guess I forgot to put my name on it, but also feel free to come talk to me also. Okay, so I'm going to just go through all of these. This is the speed at which hopefully we'll be writing our pipelines to prepare them. But yeah, you can see, you've seen different versions of this pipeline, and there's many different boxes here kind of that actually requires full teams. Like for the dark energy survey, there's large teams doing all of these different parts that kind of leads out nice parameter plot out at the end. But then for us specifically, we are roughly divided up into these 3 working groups, which include survey strategy, where some of our members were actually serving on the core community definition committees, and then sharing clustering measurement. So this is taking the pixels and products from the SOC to data vectors, and then cosmological inference that takes those data vectors and then takes us to the output cosmological parameters. And then, of course, in all of this, simulations are vital. And so, we have members of our team who have been very ingrained in, developing simulations, including the open universe. And then, of course, also at the foundation of everything, we care that everybody is productive and happy. So, yeah, there's a lot that will go into that. OK, so here, I'm not going to go through this. But we kind of have these rough phases. And so there's these scheduled releases, and there's anything from very basic functionality. We have a lot of existing algorithms and pipelines that we're trying to adapt from, as much as possible. We don't want to reinvent something. We want to reuse things and kind of adapt it for Roman. And so that's R1, but then eventually we want to get to the final data release for the year 1 data analysis. Okay, and then community engagement. There's a lot of text here, but again, we want to correlate, collaborate with a lot of other ongoing experiments on the ground and also in the sky. And yeah, we really want to enable Roman to achieve its full potential in combination with all of the other information that we will have in hand. And so here are some ways in which we're hoping to synergize or engage with people. So there's community workshops that we're planning on the high latitude imaging survey, hackathons, and then public data challenges. And yeah, at this point, I'm going to turn it over to Tim, since I wanted to kind of give an example of one of the, I guess it is the first data challenge that we've been running.
Yeah, so as Ami said, this is the first data challenge. It's coming out of the cosmological parameter inference pipeline group. The core effort of CPIP, generally speaking, is to run increasingly complex data challenges using our inference code, Kubaya Cosmo-like architecture, COCOA. And then ultimately, of course, to be running it on data. That is the final goal. This first data challenge has the goal to train all of the PIT members on using COCOA. It is not that easy to use a complex inference code. So we have generated a couple of input data vectors from this code that has different cosmologies, different systematics models, and then we're analyzing this with a baseline analysis framework. And the idea then is to study user variance, sometimes even if the code is the same and the settings are the same, there are still differences and also differences in interpreting the outcomes. It's also an idea to study parameter biases as a function of different inputs. So some of these data vectors actually do not map onto the parameter space that is being used in the analysis, so there will be biases. And then also, of course, it is important to forecast the information content of the survey now that we have new survey parameters. So we're going to do that for the HLWAS medium survey. And then we're going to release a stable version of the code for these baseline parameter analysis settings, including fast emulators. And these fast emulators should really enable you to also run some of these likelihood analyses on your laptop. And yeah, there's hopefully going to be a paper, and very hopefully by October 1st, such that it is in time for job season for the junior scientists. Yeah, it's a bit ambitious. This is an example of one of the emulators already. So you can see in orange the COCOA analysis, standard MCMC. It is also very fast, but it does take days on very, very limited number of cores. So you can, of course, run multiple of these chains in parallel. But if you want to use the emulator, and as you can see here, this is overall a 23-dimensional parameter space. Some of the parameters are shown here. The emulator is very, very precise, and you can hardly see any differences. And we're still improving it, actually, in terms of accuracy, although this is already good enough for this case. And that runs within fractions of an hour, so 15 minutes. It depends a little bit on the setup. If you run it on a GPU, actually, I've been told, at least, that it takes about 15 minutes. So we are going to use this framework now to study the impact of systematics on and of analysis choices to optimize the Roman survey. In stage 3 surveys, this has taken up an enormous amount of CPU hours. Now we're much faster. And so I wanted to thank everybody who's participating in the CPIP DC1, and especially also Jeshan, Haley, and Vivian, who've been working very hard to make this happening. Okay, very briefly, these are the old forecasts. We're updating those now. You can actually see constraints on dark energy parameter equation of state for individual probes that can be obtained from the imaging data, but then also from the spectroscopic data and the supernovae data. And this plot here in particular, I wanted to highlight because it shows the power of combining different cosmological probes. You can use these different probes to test whether they are in tension. That is indicative of new physics. And if they're not in tension, you can combine them and you do model comparison, and that is indicative of new physics as well. So I think I'm going to stop there. These are going to be updated, and back to Ami.
Okay, yeah, just wanted to say, again, come talk to us this week to learn more. And also I thought I'd highlight, so Catherine and Yoki are organizing an early career thing tonight at Nepenthe Brewing. So you could, for example, go to the SDAS happy hour and then go there. So yeah, we'll leave it there.
We have time for one question, then we can go out for lunch. There you go.
Out of curiosity, is the data challenge restricted to the numbers?
We've not thought about this as a rule. We will definitely want to make it generally available also to other surveys, of course. It's interesting. Other analysis frameworks test these data vectors and see touches on code comparison. So no, it is not restricted. I'm just going to define that as a rule now. It's not restricted.
Thank you so much to all the speakers for these